We're continuing our unit on plate tectonics, and one of the potentially catastrophic results of plate tectonics that we've been talking about are earthquakes. We talked about volcanoes happening along subduction zones and hotspots, but earthquakes, we've been moving into them and talking about measuring their magnitude and their power and their potential for damage. So if we wanted to determine the epicenter of an earthquake, we need to read through some data, we need to triangulate some things. So let's go through that. Let's see how we can determine the epicenter of an earthquake. We did this web quest where we figured out where the epicenter of a earthquake was in Japan. So in order to do this, we need to look at the P waves and the S waves. We know that earthquakes emit waves and they move over time. The primary waves arrive first. They're faster. They travel kind of as a compression wave. And secondary waves are more like shear waves. So primary waves, if you can think of having the analogy we used in class was if two people are holding each end of a slinky and one person retracts the slinky and lets it go, that's your compression wave. It kind of travels in that way. And if we're talking about secondary waves or S waves, they move slower. We said they can't travel through water, which is important. It's how we know, or it can't travel through liquid, I should say. It's how we know that the outer core is a liquid, because S waves can't travel through it as they're traveling through the earth. S waves travel as shear waves. It's like if two people are holding each end of a rope and you give it one of those, that whip-like motion. That's how an S wave travels. How do we know this? Well, we can measure the movement of these waves using a machine called a seismograph. And seismographs put out seismograms, and this is a seismogram with the waves. On the x-axis we have time in seconds, on the y-axis we have millimeters. So we can do magnitude with the millimeters, and we can do the time intervals with the seconds on the x-axis. Now, what are we looking for here? What do we need to read? Well, we said that primary waves, or P waves, travel faster. So if you have the epicenter of an earthquake and you have a seismograph that's located 100 miles away, the primary waves are going to get there first. They're going to travel faster. They're going to get there first, and they're going to start this undulation here. The secondary waves get there later because they're slower. So here's where the primary wave started. Here's the secondary. The distance in between is the S and P interval. That's going to be important here. Okay, this is the beginning, the first, the primary wave, the secondary wave. We find that interval. That tells us, that's how we determine the distance that the wave traveled from the origin, from the epicenter of that earthquake, till it got to the seismograph. So let's use this information to locate an epicenter. Let's do Southern California. Okay, so here's Southern California. We're looking at an earthquake here, and we have to use 3 different seismographs. What a seismogram, which is produced by a seismograph, what it can show you is it can show you distance. It doesn't tell you anything about direction. So once we get the distance from one seismograph, we have to use 2 other ones, triangulate each radius from each circle. This will all make sense once we see it. And then you can get direction. So we have to use these to get distance. Here's our interval once again. We're using one in Fresno. We've got a seismograph in Fresno. We've got one in Vegas. And we've got one in Phoenix. So these are where our seismographs are located. We're going to be looking at readings from those 3 seismographs. Okay, first one, here's Fresno. So we have the beginning, the P wave arriving here. We have the S wave arriving here. What's that interval? Each vertical line is 2. So we're looking at 35 seconds. Okay, it took 35 seconds for those waves to travel from the origin to the station. How about Vegas? Here's the primary wave, secondary wave. If If you look at that, you read the graph, we're at 39 seconds. Type that in. And finally, Phoenix. Primary wave, secondary wave. Looks like Phoenix is farther apart. Looks like the magnitude is lower. Not as strong in Phoenix as it was. You can see, look at the magnitude in Fresno and Vegas. So, not felt as strongly out in Phoenix. Took it 61 seconds to get there. Alright, now we have to convert time into distance. Here we go. This is what we use. So here's our times. We have to use this line on the graph to determine distance. So, time on the y-axis, distance on the x. 35 seconds. We're here. It looks like we're at 340 kilometers. The epicentral distance. The distance from our seismograph station to the epicenter of the earthquake, 340 kilometers from Fresno. How about Vegas? Vegas, we were at 39 seconds. Okay, we're looking at 380 kilometers epicentral distance. And Phoenix, took it 61 seconds. We're up here, so we're looking at about 595 kilometers for epicentral distance. So, we triangulate these. What do we get? Well, here's our different circles. We've got Vegas in the center. Here's our epicentral difference. The radius is the distance from this seismograph to the epicenter. Here's Phoenix. That radius is the difference from the seismograph station to the epicenter. Okay, somewhere in this radius. And here's Fresno. The radius is once again the distance. We got distance using that. How do we get direction? Well, we get direction from triangulating these. Once again, where do all of these circles overlap? It looks like they overlap in LA. So, where they overlap is the epicenter. And that's how you determine it. So it's going to be strongest here, which is what we kind of predict. Phoenix is farthest away. Vegas, Fresno was closest. That's how you do it.